right, I think we have the technology sorted out, but we'll get started in a couple of minutes.
Your mic's not on or you're not very loud. It's just you not loud enough.
I think it's me not loud enough. All right, so I guess it's time to get started. This is the IRTF open meeting at IETF 119 in Brisbane. My name is Colin Perkins. I'm the IRTF chair. Just like to start with the usual reminders. This is an IRTF meeting, and the IRTF follows the IETF's intellectual property disclosure rules. So by participating, you agree to disclose any patents or patent applications you have on the work or on your contributions, and that includes questions or contributions from the microphone lines. In addition, we make audio-video recordings of these meetings available. We're being streamed live on YouTube, and the recording will be on YouTube afterwards. If you come to the microphone and speak at the microphone, you will be included in that recording. And if you make comments in the chat as well, those will be recorded. If you're participating in person and do not wish to be photographed, then please wear one of the red "Do Not Photograph" lanyards. But as I say, if you speak at the microphone, whether or not you're wearing those lanyards, you are consenting to be recorded. If you're participating online, please make sure your camera and your microphone are turned off unless you're actively asking the questions. And please do use the common Meet Echo queue, both for online and in-person attendees. By participating in this meeting, you agree that any personal information you've made available to the IETF or the IRTF will be handled in accordance with the privacy policy as specified on the slide. And you also agree to work respectfully with the other participants in the meeting, and the code of conduct and the anti-harassment procedures do apply. And if you have any questions or concerns about that, either contact me as the IRTF chair or contact the Ombuds team, and their contact details are on the slide there. If you are attending in person, please scan the QR code to have your attendance recorded. Use Meet Echo to join the microphone line if you wish to ask questions. Remote participants, make sure your audio and video are off unless you're asking questions, and you can use the Meet Echo queue facility to join the queue, and we have a common queue for both local and remote participants. So this is an IRTF meeting. The IRTF is a parallel organization to the IETF, which focuses on longer-term research issues relating to the internet and its development, while the IETF focuses on shorter-term issues relating to engineering and standards making. The IRTF is a research organization. It's not a standards development organization. And while it can and does publish documents in the RFC series, the primary output of the research groups is understanding and research results and research papers, rather than RFCs, and certainly not standards documents. The IRTF is organized as a number of research groups. The currently active research groups and proposed research groups are listed on the slide here. The Crypto Forum group and the Measurement and Analysis of Protocols research group both met earlier today and just after lunch. The other groups highlighted in dark blue on the slide, the Decentralized Internet Infrastructure group, the Global Access to the Internet research group, the Congestion Control group, Information-Centric Networking, Network Management, Quantum Internet, and Research and Analysis of Standards Processes are all meeting later in this week. So please do look out for those sessions, and please go along if you're interested in those topics. As I say, the IRTF can publish RFCs. This is perhaps the most RFCs we've published between any pair of meetings since I took over as IRTF chair 5 years ago. And we've actually published 7 RFCs this time. I think 4 of them, I see Dirk over there looking horrified, 4 of them from the ICNRG in the last month or so, the ICN ping and traceroute specifications, the path steering draft, and an alternative delta time encoding draft. From the Crypto Forum group, we had RFCs on oblivious pseudo-random functions using prime order groups, and on the Ristretto and DCAF groups. And the Privacy Enhancements and Assessments Research Group also published an RFC providing a survey of censorship techniques towards the end of last year. In addition to the RFCs, we have been working on a revised code of conduct for the IRTF. That is currently in draft Perkins IRTF code of conduct. It's a draft, as you can tell, which we're still discussing in the IRSG. Please do read this. Please do comment on it, send feedback to myself, to the broader IRSG, to the IRTF discuss list. We want to get this right, so please do have a look at this, make sure it's saying the right things, make sure you have no concerns with it, and please send feedback. We're hoping to publish that hopefully in the summer. So as I say, please do send us feedback. In addition to the research groups, the IRTF also runs the Applied Networking Research Prize. This is something we organize in conjunction with the Internet Society and with sponsorship from Comcast and NBC Universal. And the Applied Networking Research Prize is awarded to recognize some of the best recent results in applied networking research. It's awarded to recognize interesting new research ideas of potential significance and relevance to the internet standards community. And it's awarded to recognize upcoming people that are likely to have an impact on the standards community and on internet technologies going forward. Over the years, we've had a number of these, we've made a number of these awards. We've had some fantastic papers, some really good awards, some really strong people. I'm very pleased to say that we are continuing that trend. We have one award today, which will go to Dongqi Han for his work on context shift adaptation and normality shift adaptation in anomaly detection systems. And he'll be giving his award talk in a few minutes. So congratulations very much to Dongqi. In addition to the prize, we also have run the Applied Networking Research Workshop, which co-locates with the IETF meeting in July each year. This year, that will be collocating with the IETF 120 meeting, which takes place in Vancouver in July. The chairs for that meeting are Jayshree Sengupta, Simone Ferlin, and Ignacio Castro. The call for papers is on the website on the URL listed on the slide. Papers are due in about a month on the 15th of April. So please do consider submitting your applied networking research work to that workshop. It's organized in conjunction with ACM SIGCOM, and the proceedings are published in the ACM Digital Library. So please do consider submitting your work. I think the final thing I want to say is that we also offer a travel grant program. And we have a significant number of people attending this meeting using these travel grants. We're very grateful to our sponsors, to Akamai, to Comcast, to Netflix, who have been involved in this program for a number of years. And new for this meeting, the Brisbane Economic Development Agency and Google have both provided significant funding, and we're very grateful because we've been able to bring a number of people to this meeting, and I think this is a very valuable thing. We will have travel grants available for the future meetings, so if you are interested in attending the Vancouver meeting or the meeting in Dublin in November, travel grants will become available, and the call for travel grant applications for the Vancouver meeting will be available in the next couple of weeks at the URL on the slide. So if you're interested in that, please do look out. And with that, that's all I have to say. The main focus of the meeting is Dongqi's award talk. So please welcome Dongqi up to the microphone, and we'll move on to the awards. Okay, so the Applied Networking Research Prize Award for IETF 119, I'm very pleased to announce, goes to Dongqi Han from Tsinghua University. Dongqi is a PhD candidate at Tsinghua. His research focuses on data-driven network management, AI trustworthiness in security applications, and other intersections of AI and network security. The paper he'll be presenting today, Anomaly Detection in the Open World, Normality Shift Detection, Explanation, and Adaptation, was originally published in the Networks and Distributed Systems Security Symposium in 2023. Dongqi, thank you. Over to you.
Okay, thanks for the introduction, and also thanks the press committee to give me the opportunity to introduce our work, Anomaly Detection in the Open World. And I'm Dongqi from Tsinghua University, and this is a joint work with State Grid Corporation of China. And as you can see from the title, this work is about anomaly detection. So let's first begin as some background. Nowadays, cybercriminals are becoming more professional and coordinate. So traditional defense systems like web gateways, firewalls, and IDS, IPS are supposed to be security enough. But now skilled attackers can bypass approximately all these defense systems. So in this context, anomaly detection has been widely used in diverse networking, network security applications for the great performance of learning without knowledge of anomalies and have the ability to detect unforeseen threats. And with the emergence of deep learning, it has been shown that deep learning has a great potential to build network security applications. So compare with the traditional algorithm, the advantage of deep learning is to learn better nonlinear and hierarchical features from complex and massive data. So the learning mechanism of deep learning-based anomaly detection is called zero positive learning. Here, positive means anomalies. So zero positive learning means the deep learning model are trained with only normal data. And typically there are two kinds of zero positive learning. So the first one is reconstruction-based learning. And this is usually achieved by generative models such as GAN, autoencoder, variational autoencoder. So during training, only normal data is fed into the model to minimize the reconstruction error between model input and model output. After training, it can detect anomalies by computing the reconstruction error, and the model is very likely to be failed when reconstructing anomalies, which are very different from the training normal data. The second one is called prediction-based models. So, which is usually used for time series or sequential data, and achieved by such as LSTM or recurrent neural network. So during training, given a normal time series with the length of t, which is 6 in this example, the sequential model like RNN will increase the probability of predicting the last sample at time t through the sequence with the last t-1 samples. So similar to reconstruction-based models, such model can predict the last sample in normal time series with higher probabilities, but wrongly predict the anomalies time series. Okay, this is the basic idea of deep learning-based anomaly detection. And so far, researchers have developed deep learning-based anomaly detection in various network security applications, such as network intrusion detection, log anomaly detection, lateral movement detection, and host-based threat detection. Unfortunately, the great success of machine learning or deep learning are based on the closed word assumption. That is, testing data must be similar to the training data, also known as the IID assumption. However, in open world settings, the distributions of testing data can change over time in many unforeseen ways. In machine learning community, this problem is called concept drift problem. Here, concept means the distribution of data, and drift means the distribution has changed. And concept drift can be quite common in security. For example, the change of statistical features of malware during malware evolution will make the performance of a malware classifier begin lower. So frankly speaking, the model aging can be one of the most frustrating problems in real-world applications built on machine learning or deep learning. And we will see the great performance on the validation side, but overwhelming false positives or false negatives in real deployment. And this will easily make people lose the faith of learning-based methods. So actually, concept drift has been well studied in the context of supervised learning. In security domains, there are some of excellent work previously investigate concept drift in malware classification, like I list here, Transcend and CADE. And in machine learning community, there are many related topics, and one remarkable direction is the out-of-distribution detection. So, sorry. So as shown in the left picture, if a sample doesn't belong to the distribution of existing classes, it will be detected as an OOD sample. However, anomaly detection models are built on purely normal data, so they are immune to the drift of malicious or abnormal distribution changes, but comes at the price of more severe impact when the distribution of normality shifts. Here, normality means the distribution of normal data. And normality shift can also be quite common for networking, for security domains, because the systems themselves and can differ and evolve over time, such as some system patches or the involvement of new devices, new users, or new protocols. And as shown in the right figure, if you only have the knowledge of normality, given a simple deviates from the normality, we cannot tell whether it's a drift of normality or it's a real anomaly. So this can be a quite big challenge for detecting normality shift. And previous work for supervised learning is not suitable in this setting. So that's why we highlight the difference of concept drift and normality shift in the title of this slide. So we summarize the first key insight is here for anomaly detection without ground truth label. Anomaly shift and real anomaly is not distinguishable. And to mitigate concept drift or normality shift problem, there are basically two pipelines. The first one, which is often used, is to periodically retrain the model with new and old data, or train a new one, a new sub-classifier to ensemble. However, we think this is not suitable for practical applications because continuous training is labor-intensive and hard to obtain the reason or the timing of shift. So the second solution is to first determine and then investigate and finally adapt to the shift or the drift. And this is our scope. So the second insight here is we need to decide whether, when, and how shift occurs before adapting models to the shift. To detect the shift, we need to figure out how to represent the distribution of data. So ideally, we want to capture the data from feature space and detect the change. However, the high-dimensional distribution is intractable in mathematics. So an alternative way is to use the distribution of model output, which is something like probabilities or anomaly scores. So in this way, we are facing one-dimensional score instead of high-dimensional feature. And so we summarize the key insight 3 is distribution of normality can be represented by the distribution of model outputs. Okay, with all the 3 insights in mind, we propose OWAD, short for Open World Anomaly Detection, and which is a framework of detect and explain and adapt to normality shift for deep learning based anomaly detection. As you can see, this is a quite big and complicated figure, and I will try to explain the motivation example in it. So suppose before any shift, we have 5 samples in blue to represent the old distribution of normality, and we fed them into the detection model to get the model outputs, which are anomaly scores or probabilities. And suppose after some shift, we collect another 5 samples in green from the new environment, from the new distribution. We also get their model outputs. And however, as we see from the picture, the original model outputs are hard to distinguish between old and new distribution because they are all concentrated between 0.9 and 1. So the first step of OWAD is to force a transformation on the original model outputs, which we call model calibration. We expect the calibrated model outputs to provide probabilistic or statistical information of the sample. So in this example, we transfer file outputs in all distribution to be the percentile of original outputs, which is 1/5, 2/5, so on and so forth. So as we can see, the distribution become more distinguishable after calibration. However, in practice, there won't be only 5 samples, so we need to compare the two distribution of calibrated outputs more strictly. So that's why we introduced the second step, shift detection. And here we conduct a hypothesis test on whether two sets are from the same distribution, and use p-value to determine whether there is a shift. So obviously, in this example, normality has shifted. The next step is to investigate and explain the normality shift. Here, our goal is to find the most important samples in the new distribution that induce the shift. We formulate an optimization problem to assign a weight for each of the 10 samples from old and new distribution. And the weight indicates whether the sample can represent the new distribution after shift. Like this. The intuition is to use the mixture of old and new distribution to reconstruct the new normality distribution, as shown here. And here we won't use all samples from the new distribution because new samples need to be labeled, and we want to lower this labeling overhead. So as shown from the feature space in this example, we use 3 samples from the old distribution and 2 from the new distribution for the reconstruction. We can also obtain some insights from the explanation results. First, these 3 samples remains in the new distribution. Then these 2 are no longer normal in the new distribution. And these 2 are newly become normal in the new distribution. After selecting the important samples, we need to label them to filter out anomalies, because we won't let anomalies go into the to the anomaly detection model. Finally, in the last step, we update the anomaly detection model for adapting to the shift. We retrain the deep learning model with the samples selected from the last step, as it can represent the new distribution. And to avoid forgetting useful knowledge when updating model, we assign different weights for each sample, which is exactly same to the weight derived from the aforementioned shift explanation. So this is the basic idea of OWAD, and note that this whole procedure can work iteratively to make sure that anomaly detection model is always up to date. Let me introduce a little bit more detail of each of the 4 steps in OWAD. And for first step, output calibration. In supervised learning, model calibration is to transform classifier scores into class membership probabilities. For example, if we have 100 predictions, which are always model outputs of 0.8 after calibration, then the ideal case is that exactly 80% of them should be correctly classified. But for anomaly detection, we don't have two class labels, so we cannot use the above accuracy-like metrics as the goal of calibration. So here we propose a new one, which is the percentile of model outputs among all training normal data. And here is an example. After calibration, we can see that the outputs are uniformly distributed between 0 and 1. So how to achieve this? Basically, we can we can select some parametric function and estimate the parameter using the original and expected outputs. So in this study, we use historic regression as the basic function because it meets all these three requirements. And about the second step, after calibration, we perform a hypothesis test on the new and old calibrated outputs to determine whether there is a normality shift between two distributions. So here the null hypothesis is that two data are from the same distribution. So this means no drift happen, and the alternative hypothesis is just the opposite. And we choose permutation test in this work as it is distribution free, support any test statistics, and suitable for small data set, especially considering we have limited new samples due to the labeling overhead. And we use the KL divergence as the test statistics and to compute the p-value. As for the third step, as we mentioned before, due to the labeling overhead on the new distribution, shift explanation is to find a small set of samples from new distribution that is important to induce the shift. We formulate this procedure as an optimization problem to solve the weight for each samples from old distribution. Sorry. And the old distribution denoted with MC, and the weight of new samples are denoted with MT. So we keep the sample if its weight in MC or MT is close to 1 and discard it if close to 0. The optimization includes 3 loss terms. So accuracy loss term indicates that the mixed samples of old and new should accurately reconstruct the new distribution. And overhead loss means to choose as few samples from the new distribution. And determinism loss means MC or MT should be deterministic, either close to 0 or close to 1. So here is an example of how the mixed distribution reconstructs the new distribution. Here, the deep blue samples are selected from the new distribution, and the light blue ones are discarded from the old distribution. And for the last step is to make sure that the model can adapt to the new distribution. So we update the model with the samples selected from the last step, and here we show the new loss function when updating the anomaly detection model. So besides the original loss function of anomaly detection model, we also introduce another loss term to consolidate important model parameters by assigning importance weight to the model parameter. The intuition here is to keep the important parameter with useful old knowledge and change the ones that are out of date. Okay, so due to the time limit, if you are interested in more detail of OWAD, please refer to our paper. Let's move on to evaluation. We evaluate OWAD in 3 security applications: detecting network intrusions, log anomaly, and lateral movement. And we use representative detection systems from top-tier security conferences. We select data sets with a long time span in months or years to reflect the normality change in a long time period. And we detect normality shift periodically according to the time span of each data set. So the first question we ask here is whether normality shift occurs in these security applications, and the answer is yes. From the shown figures, which are the distribution over time, we can observe that normality shift in security domain is quite common and different for each application. So a case-by-case analysis based on our explanation method is necessary. Next, we perform an end-to-end performance evaluation after adapting to the shift and observe to which extent the performance of model is improved by OWAD and other baseline methods. So as shown in this figure, we simulate a scenario and split the data set into different time points, which is T0, T1, T2, and so on and so forth. In T0, training set is used to train the original anomaly detection system. And in T1 and later, validation set is used to detect and adapt to the shift, and test set is used for evaluation. We also conduct two experiments to evaluate the end-to-end performance. First one is called single adaptation, is to adapt to the shift only one time and observe the performance in subsequent time points. The second one called multiple adaptation is to detect and adapt at each time point. From the result of single adaptation experiments, we fixed the budget of label as 30%, which means all methods, including OWAD and baselines, can only use 30% labeled samples at most for updating the model. And here, y-axis is the model performance, which is higher the better. And the highlight right line is our method OWAD. And we can observe that OWAD outperforms other approaches at the adaptation time, namely T1 or T2 here, and also can mitigate the performance degradation in subsequent time points. So in multiple adaptation experiments, we relax the budget of labels to observe the labeling overhead together with the model performance after adaptation. So the lines here are the performance after shift adaptation, which is higher the better, and the bars here are the labeling overhead, which is lower the better. And the conclusion is that OWAD can achieve better results with significantly less required labels. We also observe the number of false positives and false negatives before and after adaptation. And the conclusion is that OWAD is the only approach that can reduce both false positives and false negatives. Next, to show the potential of OWAD in real-world applications, we conduct an initial deployment on a SCADA system. Here we worked with state-grid Shanghai Electric Power Company, and this company provides electricity transmission and unified control of Shanghai power grid in China. What we do here is to assist their so-called security monitoring system with our method OWAD. And this security monitoring systems will continuously monitor and analyze logs or events from all the devices in the grid. And so the problem is that it turns out to be very effective at the very beginning, but the performance of these security monitoring systems are soon become very low during long-term deployment. So that's exactly what OWAD want to deal with. So we deploy OWAD upon their system to detect and handle normality shift. We have collected over 10 million logs from 20 devices in 5 months, beginning at October 2021, I guess. So we deploy OWAD shift detection first, and as shown in this two figure, so the left one is in 3 weeks, and the right one is about 4 months. And from the result, we can say that the left figure is not shifted, and the right one, which is 4 months, is obviously shifted. So next, OWAD will perform shift explanation to find the reason of this shift. As a result, after identifying the important shift logs, we finally get 2 important logs. The first one shows network volume increases for some devices, and the other one shows that there are new service continuously being launched. So after talking to the operator, we finally found the key reason is there is a big system update and many devices are restarted at about January 2022. So there are some FTP service errors due to this update and restart, and finally cause this normality shift. So finally, after performing the last step of OWAD, which is shift adaptation, we successfully reduced over 90% of false positives caused by the shift. Okay, here are some takeaways. The first one is normality shift is quite common and complicated in network security domains. And the second one is we found that the model outputs in security domains are highly uncalibrated. So after using the calibration method proposed in this work, model outputs can effectively represent the normality distribution. The third one is if we want to handle normality shift for anomaly detection model, labeling is inevitable. This is a key difference from concept drift problem in supervised learning. But the good thing is that OWAD can achieve better performance with lower labels. And the last one is OWAD is shown to be able to reduce both false positives and false negatives. We have released our source code on GitHub, and you can try it for your own anomaly detection applications. Okay, thanks for your attention, and I'm ready to take questions.
Thank you. All right, does anyone have any questions for the speaker? Surely somebody does. Okay, so I see Yaron Scheffler.
Yaron Scheffler. Thank you for the presentation. Very interesting. Could you speak a little more about the labeling, the amount of labeling, maybe in the specific experiment that you discussed, and what level of expertise is expected from the person doing the labeling?
Okay, that's a good question. So, okay. Oh. Okay. Okay. So the labeling is a key step between shift explanation and shift adaptation, because shift explanation will give us some important samples induce the shift, and we need to filter all the anomalies because the anomaly detection model here is only trained with normal data. So I think you are asking about in practical applications, what is the labeling overhead, right? In the public, in the experiment of using public data sets, I think in network intrusion applications, we need to label about 5,000 traffic flow half a year. And for log anomaly detection systems, it's a little bit complicated. We'll need some more labeling overhead, but the good thing is the system logs are turns out to be there are many same or similar logs, so this will reduce the labeling overhead. And for our deployment in SCADA, and to find these two important logs, it just take hours of an operator. Yes.
Thank you.
Okay, thank you. Brian Trammell.
Hi, thanks for the talk. This was super interesting. My question is a related question, but it's over on the data collection side of things. I might have missed it, but sort of like the initial data that we sort of like boot this system with, right? Like, so both the before shift and after shift data, that is all data that is considered normal, right? Like, so this is like a zero positive system. Am I correct?
Yeah.
Where do you get the normal data from?
This is a good question, because we need, in this research area, we must make some assumption. Is we during some time period we can collect. We suppose there are no any attacks or any anomalies. So we
during that period, would you actually have somebody who's doing the labeling come by and sort of like do a sniff test, or you just sort of assume that that's the case, and then you let the feedback loop with the labeling step sort of push that out of the system?
Yes. So your question?
So like, so you're making the assumption on the front end that you have some data that is attack free, which is, you know, we can talk about the validity of that assumption. Do you actually have somebody check that, or are you assuming that the reinforcement loop is gonna take care of that for you?
So it's like a reinforcement learning framework.
Okay, cool. Thank you very much.
Okay, thank you.
Alexander.
Hi, I'm Alexander Railan. My question is about this explanation. Could you help me understand it better? In one of the last slides, there was an explanation that an anomaly was detected, and this was because of an FTP server update which went wrong. Was that explanation generated by the system or by the human?
By the system. We formulate an optimization problem, and it can automatically, by serving this optimization problem, it will automatically give us some samples that indicating the shift.
Wow, very impressive.
So the system said it was FTP, or the system showed the system identified some traffic, and the user then went, oh, that's obviously FTP.
FTP.
So is it the system which says this is this FTP service or whatever it was causing the problem, or is it the system that says this is an example of the traffic flow which caused the problem, and the user then says, oh, it's this application?
Oh, I see. It can just read some samples, some data. If we like the input of the model.
Okay. So it finds exact representative samples of the problematic traffic.
Yes, the deep reason needs some security operator to investigate.
That's still very very helpful. Can you maybe obviously it's the goal is that it finds significant samples and uses those to shift the distribution. How sensitive is it to that process? If that process is imperfect and it finds perhaps the wrong samples, does that significantly affect the performance, or is it somewhat insensitive to this? It just takes adapts maybe a little slower.
You mean when OWD makes some mistakes?
Yeah, right. If its process of finding the significant samples is imperfect, does that really throw it off, or is it just is it really sensitive to this process's accuracy, or is it? Or, I guess have you evaluated how sensitive is it to this process's accuracy?
Yes, I have evaluated the robustness of the explanation. So if you add some small noise on the original inputs, so what it will be in the model outputs. So the result turns out to be it's okay about such small noise.
Okay, thank you. Hannes.
Hi, Hannes. Could you say a little bit more about your experience with the SCADA system? What type of traffic was that? Is that traffic that is where you did the training, was that sort of always very similar, or was that some sort of had a lot of irregularities, and so you knew upfront on how much you need to train it for to get to sort of have a good starting point, so to speak?
So what I research here in this work is a generic network intrusion system. So it can be many different types of traffic, and the normal traffic I think is universal because we are attack free. So we just collect some traffic that is does not include some attacks, some anomalies, and theoretically we can detect any attacks or anomalies deviates from such normal traffic.
But for example, you mentioned in one of your applications, you had this, if you go back a little or forward, I don't know where it was.
This one?
Yeah, background SCADA system and state grid. So for some of the, at least the communication protocols I've been working with, some of them had sort of sensors and actuators involved, and so a lot of the interaction that you see on the network depend on what happens in the real world, so to speak. Like the actuators, obviously, if someone does something, or the sensors if certain events are triggered. So the traffic is sort of, it's somewhat hard to say what is the normal traffic. Like, so I'm curious on what your experience was with some of those type of systems where it's not always the same pattern, like you had in your example when something failed, but that may be just a sort of some sensors not triggering some interactions, like you have some motion detection sensors, and sometimes there is just nobody. It's very infrequent, right?
Yes, I agree with you.
Yeah.
So I think this is a common problem for anomaly detection. We need to clearly define what anomaly is and what normality is. So, and anomaly detection algorithms can only work better in some clearly defined problem. We know very clear about what anomaly is, and the normality is very stable. This is very important for anomaly detection. Otherwise, there were overwhelming false positives.
Okay, yeah, that's what I'm worried about, the false positives, huge number of false positives.
Yes.
All right, thank you. Are there any final questions from people? I guess I have one while we're waiting there. obviously this is an IRTF meeting, and we're co-located with the IETF and the standards body. Is there anything that you think the IETF or the standards community or perhaps the operator community could do to help facilitate this type of research?
Could help to.
It could help make this sort of research, this type of system work better. Is there any, you're in a room full of people who operate networks and who standardize network protocols. Is there anything we should be doing differently to make this sort of problem easier? I mean,
It's a big question.
I guess one of the things would be providing test data to test against, but is there anything else we could be doing?
Let me see. I actually I have no idea about it. Sorry.
I guess data is probably the main thing.
Maybe I can think later about this.
Sure, absolutely, absolutely. All right, Chin.
Just try to answer Colin's question. Actually, in IETF, they currently formed a new working group focused on, it's NMOps actually, and there's some, AI-related topic. They, focus on anomaly detection, and maybe one use case is, for example, SRv6 visibility or these kind of cases. So they can use AI to, detect some anomaly. So just before this meeting, we have, 3 drafts, try to explore, incident terminology, incident management, and also metadata connection for anomaly detection. I think seems can synergize with your, can leverage some research results. I think you can consider whether you willing to contribute, for NLOps. Yeah.
Thank you, Rüdiger. Sorry.
Rüdiger Volk, for a quarter of a century operator, a couple of years ago. I think I heard you answer to Hannes that you need to know what is an anomaly, right? Or did you say you need to know what's normal? Well, okay, kind of two sides of the same thing. As an operator, I view anomalies as something that is unexpected. Yeah, well, the operational question becomes, well, okay, how sure can I be that anything that is anomal actually triggers an alarm?
Okay, thanks for the good insight of anomaly.
All right, thank you. We are about out of time, so thank you very much for the questions. Thank you very much for an excellent talk. Congratulations again on the award, and thank you again. All right, so that's all we have today. Please do consider submitting your papers to the Applied Networking Research Workshop, which will be happening at the IETF in July in Vancouver. And we'll also have a number of ANRP talks there as well. So thank you, everybody. And that's everything for today. Thanks all.